All right, gang, Math 6610. I'm going to jump into two-way ANOVA, sometimes called factorial ANOVA. And this process can be extended into 3, 4 K-weight ANOVA. But I haven't decided yet whether I'm going to demonstrate the three-way ANOVA. I don't think I would ever uh, carry out a four-way ANOVA. I think the interactions would be absolutely insane. But I don't know. Maybe there'd be a research question that would require that. So anyway, let's focus on two-way ANOVA. What you should have on your radar, the way you can identify one of these, is you'll have two independent variables. Both of these will be categorical. So I'm going to call this variable A and variable B. Again, both A and B are categorical. And my dependent variable is quantitative. I will call that my variable Y. So the overarching question here is kind of threefold. What source impacts the variation in Y? Again, variation, ANOVA, obvious connection there. So is it variable A? Is it variable B? Or is it variable A cross B, or the interaction of A and B? Now, if we were just focused on A, then we would just have a one-way ANOVA, right? But when we bring in that second layer, that second categorical variable, uh, then we get into the two-way ANOVA family. So an example of this may be if we were looking at maybe the difference in maybe ACT scores over school districts, maybe school districts A, B, and C over gender. Maybe gender is male, female, non-binary, however we may classify that. So again, these must be categorical, and our dependent variable must be quantitative. Now, first thing we start with is we start with a table of the marginal means. And so typically in a one-way ANOVA, I would just be interested in, for example, the row means or the column means, because I only have one independent variable. But when I get into a two-way ANOVA, my focus really turns to the interaction. So A cross B, if you will. So I want to know the mean of the Y values when A is equal to A1 and B is equal to B1, and when A is equal to A2 and B is equal to B3, I want to be able to find those. Now, it takes a little bit of work in in R, and I've already done this for you. So what I have over here is I have this data set already loaded in R. And the very first thing I would want to do is I would want to take a look at my independent variables. So I can see that A is partitioned into two levels, A1 and A2. The sample size in each one of those is 9. B is partitioned into B1, B2, B3, and each one of those is has sample size 6. Now, to get the if we're going to get the means of just one variable, we can use the tapply function as we've done before, but it takes a little bit more work to get the cell means. So what I did here is you can see I messed it up here. I had a parentheses out of whack. But so I've calculated the cell means using the with function. So I must tell it what data set I'm using. Then I come in and use the aggregate function. Y is the dependent variable. Then I use the by list AB, so I can get the submeans, if you will. And then FUN just stands for function mean. So you can see that A1, B1 is 6, therefore we have a 6 there. A2, B3 is 14, so lines there. Now, another thing I may want to do is do exactly the same thing, uh, but instead of cell means, I may want to do cell counts. Got fat fingers today. So I still want all this to be the same, but I want the function to be the length. I think I have to add another. So cell counts would be 3, 3, 3 across the board. So this tells me I have a balanced design. Now, you get into some wacky stuff with the calculation of the sum of squares. There are three different ways that R calculates the sum of squares. I tell you what, let's hold that for later. Let's just focus right now on the calculations if we have a balanced design. So anyway, I have the table of marginal means right there. Now, the next thing I'd want to do is I want to get into partitioning the variance in Y into chunks. And I actually take the total variation and partition it into 4 chunks. I look at the sum of squares for factor A, the sum of squares for factor B independent of factor A. I look at the sum of squares for the interaction. I look at the sum of squares for the error. And then all of that will add up to the sum of squares for the total. Ultimately, what I want to be able to do is I want to be able to present my results in a table that looks very familiar to the one-way ANOVA. The only difference is now we have these 3 sources of variation in addition to the error, and of course it all adds up to the total. And it turns out it's a very straightforward process. So nothing fancy. It's just almost what I think you would probably expect from just studying a one-way ANOVA. So we're going to partition. I think this graph is very helpful to get a visual. We're going to partition our sum of squares total, first of all, into our explained variance versus the unexplained variance, which we call the sum of squares model, plus the sum of squares error. This is sometimes called the sum of squares between, and the sum of squares within. The sum of squares model partitions into 3 parts. And somebody's phone is ringing, distracted me. So the sum of squares model is the sum of squares for the A plus sum of squares for the B plus the sum of squares for the interaction. So let's just dive into it. Sum of squares for the A is pretty much exactly what you would think it would be. It would focus solely on the means for A1 and A2. The sum of squares is going to take the sample size and examine the difference in this mean and the grand mean and take the square of that. That's exactly what happens here. We take the sample size times the mean of A1 minus the grand mean squared plus, whoa, I'm in the wrong one, okay? I wonder, why do we have 3 terms? So again, we have A1, A2, so K equal 2 here. So works out nicely where the sum of squares for A is equal to 32. Same thing for the sum of squares for B. We focus on these values, the difference between 6.5 and 9 squared, the difference of 8.5 and 9 squared, again multiplying by the cell count, which we got earlier. And it turns out the sum of squares for B is equal to 93. I stole this data set from someone. Well, I didn't steal it, but I borrowed it from someone on YouTube. And the reason I liked it so well is because the sum of squares turned out to be nice calculations. So very little rounding errors other than once we get to the sum of squares total, where we use the variance for, well, I'll show you that in just a second. Okay, so I wish I knew who did this so I could give them credit, but I like whoever you are out there, I like your data set, so I'm using it. Now, the next thing we would get into would be the sum of squares for the model. And the sum of squares for the model actually examines the difference in each of the cells. So it takes the mean of this cell minus the grand mean times its sample size, this cell minus the grand mean squared times its sample size. So the sample size in each cell, as I found in the previous command, cell counts in R, was 3. So again, I just take each cell mean minus the grand mean, sum this up, and I get 132. Next thing I'd want to do is calculate the sum of squares total. Sum of squares total is just the variance of all the scores. It's very easy. So 11.764. Notice I made an arithmetic mistake here. Instead of n minus 1, I used n, so make sure you subtract 1. Don't do something silly. And again, the sum of squares total turns out to be a nice number of 200. So limited rounding issues. So from there, I can easily find the sum of squares for the interaction by just taking the sum of squares for A and sum of squares of B, subtracting those from the sum of squares model. And I end up getting 7 for the sum of squares for the interaction. Again, I like this data set because the sum of squares turn out to be nice calculations. Okay, so let's focus to the degrees of freedom. As you probably would think, remember the degrees of freedom for the between for a one-way ANOVA was just k minus 1. Well, it turns out it's the same for the degrees of freedom for the factors. So there were A1, A2, so we have 2 factors, degrees of freedom 1. B has three levels, so degrees of freedom here would be 2. The degrees of freedom for the interaction is just the product of the 2 degrees of freedom. Degree of freedom A times the degree of freedom B. So in this case, 1 times 2 is 2, and degrees of freedom for the total is just our grand sample size minus 1, which would be 17. All of this has to add up to the degrees of freedom for A plus the degrees of freedom for B plus the degrees of freedom for the interaction plus the degrees of freedom for the error have to add up to the total degrees of freedom. So we can easily calculate the degrees of freedom for the error by taking the total degrees of freedom minus the sum of the degrees of freedom for A, B, and the interaction, and get 12. So once we get that, the overall how we partition out the variance and present it in a table is just as you would think it would be, with one little caveat, I think. Put in the sum of squares first, then put in your degrees of freedom. Then your mean square has to be your sum of squares divided by its degrees of freedom. So 93 divided by 2 is 46.5. 7 divided by 2, of course, is 3.5. To calculate the F statistic, this value is going to be the sum of squares over the sum of squares for the error. So this 5.64 comes from 32 divided by 5.67. The 46.5, this 8.2, will be the sum of squares divided by the sum of squares for the error. So 46.5 divided by 5.67. The 0.62 comes from the mean square. I think I misstated. I think I said sum of squares. The 5.64 should come from the mean square of the factor A divided by the mean square error. The 8.2 is the mean square for B divided by the mean square error. The 0.62 is the mean square for the interaction divided by the mean square error. So we always divide by this term to get the F statistic. Then to calculate the p-value, PF, so let's just do the calculation for B, for example. So I'm going to have 8.2. Degrees of freedom here would be the 2 and the 12, because that's the way we made the calculation. So 0.0057 is the calculation of the p-value. All right, so that's the way, simple stuff. It's very easy to calculate these by hand. But as you may imagine, we typically don't. We use R. So if I am going to calculate the partition out the variance for Y as it's explained by A, B, and A cross B, the interaction of A and B, I would do very similar to what I've done before. I would use the AOV command. I would have Y as A plus B plus A cross B. So the A interact B. So I'm just going to go summary of my model. And hopefully I always hold my breath at this point, hoping that I didn't make an arithmetic error and have to end up redoing a video, but you can see that the numbers match up. You know, actually, I believe that we can just do this. I should have looked this up beforehand. Yeah, turns out that that you can just put that instead. All right, cool. So that saves you about 1.2 seconds of your life, not typing the A plus B. Now, what would be the next step? Well, the next step is we would focus on this term. So anytime I run a two-way ANOVA, I have tunnel vision on the interaction. If the interaction is statistically significant, I ignore the main effects. So A and B are referred to as main effects. This is our interaction effect. So again, if this is statistically significant, if the interaction is statistically significant, I ignore these two main effects. In this case, the interaction is not statistically significant, so I would rerun the model. With only the two main effects. So then that would become ultimately the model that I would use to explain this relationship. So what I look at with A, since I have a variable with two levels, well, I would look at a unpooled t-test. Well, what I look at for B, since B has three levels, I would run an ANOVA on B. So t-test, so I would want Y over A. And I see that I do not have statistical significance. Then I would run an ANOVA of Y over B. I'd want to run this. So anyway, I'm going to get into an example of that later, but just want to give you an idea of what I would do. I would dive into each of these effects, each of the main effects independent of the other. But I'll go through a thorough example. The interesting stuff comes is when your interaction is statistically significant, because then you know that the primary source of variation that you want to investigate is within the interaction cells. All right, gang, all I got. Take care.